Okay, good. So hi everyone, and welcome for this seminar. So today we have the pleasure to receive Sebastian Garcia-Saenz from the Southern University of Science and Technology in China. So Sebastian will talk to us about black hole scalarization with spontaneous symmetry breaking. We will have time for questions at the end, but feel free to ask questions also during the seminar, either by speaking out, or also, if you prefer, by writing in the chat or raising your hand, and then I will say the question out loud. So thanks again, Sebastian, for being here, and the floor is yours.
Okay, so I'll start by saying thanks for the very nice invitation. It's we don't often get the chance to present our work with groups in Europe, so it's very nice of you to allow for this online format. So I'll be talking about these three relatively recent papers with my group and collaborators here in China. So this is my plan. I'm going to be talking about scalarization of black holes and numerical evolution of scalar clouds, specifically in the context of the Einstein-Maxwell scalar model that is especially well known to people in this audience, of course. So I will make a quick aside in the middle to discuss a new scheme we've been exploring for the evolution of black holes in numerical relativity. Then I will present some results for the dynamical evolution of the scalar clouds that form as a result of scalarization. And then I will switch gear a little bit to discuss the combination of scalarization with superradiance. So I don't think I need to introduce scalarization to this audience, but I'll do it anyway, just to set the stage. So we understand that scalar fields, when you put them in the vicinity of a black hole, they will acquire some sort of effective mass that depends on the distance from the black hole. And this effective mass, even if it's positive definite, the mass square, I mean, positive definite on flat space, the interaction with the background, with the geometry, may make it negative, at least for some range in the space-time. If we're thinking about spherically symmetric, by the way, I will be talking exclusively about spherically symmetric black holes in this talk. I really have nothing to say at this stage about spinning black holes. So the relevant parameter for the geometry is going to be just the radius, the distance from the black hole. So if this is true, if this condition holds, then we say that the field undergoes what's called a tachyonic instability. So this is nothing but a fancy word for this condition, for this type of instability. And the expectation is that this will lead to the formation of some kind of condensate, a scalar condensate. So this is the picture over here. The trivial vacuum here with phi equals 0 is unstable. It has a maximum, a local maximum. So in the language of symmetry breaking, we would say that the scalar field, the vacuum expectation value of the scalar field becomes an order parameter for something we can interpret as a phase transition, with the scalar field eventually settling into a stable minimum, a locally stable minimum. So in some models, we expect this condensate to become stationary. This is what I call, there is some, I'm not sure if this is a standard terminology, I should say, but at least in my terminology, to make it clear from the outset, this is what I call scalar hair. So if the scalar condensate that results from the process of scalarization is stationary, I will call that scalar hair. Now we know, because there's a long suite of no-hair theorems, we know that these type of models are actually special. They are the exception rather than the rule. It's not so easy to evade these no-hair theorems. So more generally, we would not expect scalarization to actually lead to scalar hair, but it will lead to some condensate that will not be stationary, because it will either or both radiate to infinity or become accreted onto the black hole. So this is what I will refer to as a scalar cloud. So a condensate that's not stationary. So it will eventually become depleted via radiation and accretion. So a more mathematical way to say the same thing is that if you were to analyze these equations in the linear regime, you find that scalar clouds have a set of well-defined quantum numbers in much analogy with the familiar hydrogen atom, except that the spectrum is in general complex. So this is a manifestation of the fact that these are not stationary. So this has been called gravitational atoms in the literature. So I'm talking basically about the same thing. So there are many mechanisms for scalarization. The original one by Damour and Gilles. They propose what's now called matter-induced scalarization, where you have an additional scalar field on top of GR plus some standard matter fields. So here psi is some standard matter field, can be anything really. And you are postulating a non-minimal coupling by modifying the effective metric seen by the matter in this way. So F is some function of the scalar field, and therefore the matter field will see an effective metric that's modulated by this scalar field. So this is the original proposal. An alternative to this was proposed later. This is now called curvature-induced scalarization, where you actually do not rely on the existence of matter. So this postulates a direct coupling, a non-minimal coupling, I should say, between the scalar field again and some higher curvature corrections. So in particular, we like the Gauss-Bonnet term because it does not introduce additional degrees of freedom, but in principle you could consider more general things. So the general idea here is you have the scalar field directly coupling to higher orders in the curvature. So this is nice because it does not rely on additional matter. So this is something that you would observe even for vacuum black holes. However, the problem with this curvature-induced scalarization type mechanism is that it's kind of messy. The Gauss-Bonnet term, it's kind of messy to deal with, especially in numerical simulations, in fully nonlinear simulations. So an interesting alternative proposed by Carlos and other people in the group in Aveiro is what I call non-minimal matter coupling, which is it's similar in spirit to the Gauss-Bonnet coupling that I just showed, but now the non-minimal coupling is between the scalar and some standard matter field. Okay, so this could be some standard model field. Psi doesn't have to be anything exotic. This is what makes this coupling especially nice. So this is different from the minimum from the matter-induced scalarization, in that we are not really touching the coupling between standard matter and gravity. So that can be preserved according to the minimal coupling prescription. So this is particularly nice because you are not in some sense you're not saying anything about standard model fields. So standard model fields can behave perfectly in a perfectly standard way. And there's another mechanism called spin-induced scalarization, but as I said before, I will not say anything about spin, so let me not talk about that. So scalarization has been mostly studied in the case of a real scalar field, but this idea of thinking about scalarization as a process of symmetry breaking kind of naturally suggests generalizations where you can consider more interesting symmetry breaking patterns. So in the case of a real scalar field, you would have the breaking of a set2 symmetry, which is a discrete symmetry, which is kind of boring. So a natural generalization would be, say, a U1 symmetry, where you have for example, a Mexican hat type of effective potential for your scalar field. Okay, obviously you don't need to stop here. You could consider non-abelian symmetries, but in the spirit of exploring this idea for the first time, the case of U1 seems very natural and simple enough. And but it would be very interesting to see if other types of continuous symmetries could lead to new signatures. So this is the model I'm going to consider. So this is the EMS model for Einstein-Maxwell scalar. So this has been widely studied in the literature. Again, the only novelty that I'm going to introduce, which is not really a novelty, other people have considered this before, is that I'm going to make the scalar field complex. Okay, that's all. And I'm going to impose that the non-minimal coupling between the scalar field and the electromagnetic field in this case. So remember, in the spirit of this non-minimal matter coupling induced scalarization, we would like the matter field to be as standard as possible. So in this case, a very natural choice would be just the Maxwell field of electromagnetism. So this vector field here could be the standard model photon, for instance. So I would like this theory to be U1 invariant. So I'm going to impose that this coupling has to be of this form. So it has to couple through the norm of the scalar field. So this has an obvious global U1 symmetry where this phase is a constant. So I should point out that this is unrelated to the local electromagnetic U1. So this really has two symmetries. There's the electromagnetic U1 symmetry, the local gauge symmetry of electromagnetism. And we are on top of that postulating this global U1 symmetry for the scalar field, okay? Now, obviously it would be something very natural that you might want to do is, well, to make the two U1 symmetries the same. So this would amount to saying that the scalar field is charged under the electromagnetic U1. So this is something I will consider in the second part of the talk. In the first part of the talk, I'm going to assume that phi is uncharged. So this global U1 symmetry has nothing to do with the electromagnetic U1 symmetry. So this model, again, was studied by the group in Aveiro a while ago. So they were the first to highlight the virtues of this model for the purpose of studying the process of scalarization. So this is I should say that I'm not claiming this model to be realistic. I should say for me it's more of a proxy model. So we would expect any lessons that we can draw from this model will hopefully translate into more complicated models such as Gauss-Bonnet, such as non-minimally coupled Gauss-Bonnet, for instance. Okay. So if you want to evade the no-Hertz theorems, there are some technical assumptions in the no-Hertz theorems. So two conditions are this so there are some conditions on the non-minimal coupling function that you need to satisfy in order to be able to evade the no-Hertz theorem. So these are some technical assumptions. If you read through the papers by Bekenstein, there are several technical assumptions in those theorems. And it was pointed out that, well, you can relax these assumptions. And in the case of the EMS model, this translates into these conditions. We also want to impose that Reissner-Nordström is a solution of the theory. So this imposes an additional condition on this function f. So this should admit a vacuum corresponding to just a pure Reissner-Nordström with zero scalar. And well, a simple function that satisfies all these conditions is this exponential type function, which was also considered by Carlos in the original paper. I'm not claiming this is a particularly natural choice of the function f, but it is nice because it's simple enough and it has just one parameter. So that's why it's particularly nice, I think. So this is the function I'm going to consider, this non-minimal coupling function. So one can calculate the effective mass for this system, for the scalar field in this system, and one finds indeed that it is not positive definite. Whenever this coupling constant alpha is positive, you find indeed that there is a negative effective mass square. So this is remember that this is sort of intuition drawn from the wave equation that you would read off in flat space. So this is not really a very rigorous diagnostic of the presence of tachyonic instabilities. A more rigorous thing that you can do is to actually solve the quasi-normal mode problem. So you solve the equations for perturbations with physical boundary conditions, meaning that the waves have to be ingoing at the horizon and outgoing at infinity. So this is a more rigorous way to establish the existence of instabilities. And indeed, you find that there exist tachyonic instabilities. So in this language, it would be characterized by modes with positive imaginary part for the frequency. But it also tells you that the intuition from flat space is not 100% correct, because there's actually a lower bound on the coupling constant alpha. Okay, so it is almost correct, but not quite. You need to impose additional conditions on the coupling constant, and it turns out to be 1/4. Okay. So this is the picture. So we have Reisner-Nordström solutions which are unstable. They have tachyonic instabilities. So we understand that they will evolve into scalarized black holes. Remember, in my language, what I mean by scalarization is not necessarily the formation of scalar hair, but the formation of a scalar cloud, which again is not necessarily going to be stationary. Okay. Now, another observation is that these scalarized black holes are not necessarily themselves stable. So you can evolve into a solution which is itself unstable. Okay. So in other words, there exist scalarized black holes, so black holes with non-zero scalar field profile, which are themselves unstable. So in this picture over here, you can see the effective, here I simply want to draw your attention to the effective potential. So these are the solid curves. The green curve is the Reisner-Nordström black hole, the effective potential for the scalar on the Reisner-Nordström background. It has a negative potential well that explains again the tachyonic instability. But now you can also look into the effective potential on the background of a scalarized black hole, and you generically, for some range of parameters, not generically, but for some range of parameters, you can also find that the potential is not positive definite, but it can also develop negative potential wells. So the natural question is to ask, well, what happens to these unstable scalarized black holes? So the expectation would be that they evolve to another scalarized black hole, which will be stable up to the process of accretion and radiation. So this is the question we wanted to explore through numerical relativity. So we would like to, starting from some unstable scalarized black hole, we want to evolve the whole thing numerically without any approximation and see what we get. Okay, so this is the setup. So before I show you the results, let me make a quick aside on numerics. I should say this is going to be quick, mostly because I'm not really an expert. I should say that this was my postdoc Wang Zhou who did the heavy lifting with this work here. So as I just said, we are interested in the fully nonlinear dynamical evolution of this type of systems. Now there's a technical problem related to scalarization in the EMS model, but more generally in other systems as well related to scalarization, is that the instability rate can be very slow. So for example, in the EMS model for the coupling, the non-minimal coupling constant of order 1, you would find time scales of order 10 to the 4 in units of the black hole mass. And as you know, long time simulations are problematic in GR because you have constraints. And constraints are problematic because you need to keep them zero. And typically your numerics will not want to keep them zero. So constraints are problematic in long-time simulations. Now, this problem was, of course, appreciated long ago by people in the field. So there's a suite of numerical relativity schemes specifically designed for this issue, such as BSSN or CCC4. But we actually found that even though they do serve the purpose of giving you long enough time simulations, for timescales that are very long, as you would like to achieve when studying scalarization, this is not necessarily enough. So this is what we find. So in these plots here, we are illustrating the evolution of a Schwarzschild black hole. So this is just a Schwarzschild black hole. It's the most boring possible system that you can consider in numerical relativity within the so-called BSSN formulation. The four panels simply mean that we were playing here with different numerical parameters. So the details is not important. In the first one, we were playing with the maximum size of the simulation. In the second one, we were playing with the grid size. The third one, we were playing with some damping parameter for the noise. The third one, the last one refers to the step of the time evolution. Really, the details don't matter. All I want to draw your attention to is that we, regardless of your choice of numerical parameters, we find that the simulation crashes at timescales of order 10 to the 4 in units of the black hole mass. And as I told you before, 10 to the 4 is something you might foresee to have if you're interested in simulating scalarization. So we started playing with these numerical schemes, and we found a choice that we call we call it a new scheme, although really it is in the same spirit of the so-called CCC4. We call it CCC3. So in the CCC4, the basic idea is that you take your GR Hamiltonian and momentum constraints, and you don't set them to 0 from the outset, but you actually promote them to dynamical variables, and you let them evolve. You let them evolve according to some wave equation, so that your whole system is hyperbolic, and hopefully you hope that the evolution will keep them under control. So this is the idea of the CCC4 in a nutshell. Now, what we found is that actually you might actually do better by not evolving the Hamiltonian constraint. So this is something we found by playing with this scheme. Another feature of the CCC4 is that the constraints are evolved, but you also introduce some amount of damping for these constraints. Again, the idea being that you want to keep the constraints are supposed to be equal to 0. So if you want to evolve them numerically, you should make sure that they stay close to 0. So a clever way to achieve that is by introducing damping. However, this damping can also be dangerous because the evolution equation for these dampings, they are meant to be wave equations only when your geometry is close to flat. But if you have a highly curved space-time, what you thought was a wave equation may look actually quite different from a wave equation. So your damping can actually be a curse and not necessarily a blessing. So by playing with this, we also found that damping, you might want to try not using damping when you're dealing with highly curved spacetimes. Okay, you're probably asking, well, what is the rationale for all this? The answer is I don't know. So to me, numerical relativity is a bit like cooking. So we try different things and we see what works. So these are our results. So this is basically what I just said, but now in equations. So these equations are the usual CCC4. The set here, the set vector here are the constraints, the GR constraints. So when you project it on the normal direction, you get the Hamiltonian constraint. When you project it in the when you project it on the slicing, you get the momentum constraints, and you include them in the Einstein equations in this fashion. And the set satisfies some sort of wave equation. And this kappa 1 is the damping parameter I mentioned before. So what we are proposing is that, at least in this setup, I should say we are not saying that this CCC3 scheme is necessarily the best in all kind of applications, but for our applications, we found it to be the best. So what we are proposing is that you want to set the Hamiltonian constraint exactly 0, so you don't let it evolve, and furthermore, we set the damping to 0. So we found this to be particularly good for this type of systems. So this is again, this is the Schwarzschild black hole in our scheme. Again, the 4 panels simply mean that we were playing with different numerical parameters. What I want to draw your attention to is the vertical axis. So this is the horizon radius, which should equal 4 in the units we are using. And you see that on timescales of 10 to the 5 in units of the black hole mass, you get an error of order sub%. So this seems very good for such long timescales. So the previous one was a Schwarzschild black hole. This is now the process. This is now a scalarized black hole. Sorry. And again, we obtain consistent results. On the left, you have the BSSN, which crashes on timescales of order 10 to the 3 in this case. In the case with scalarizations, whereas our proposed formulation does much better. So it appears stable, relatively stable on timescales of order 10 to the 5. Okay, so let me go back to physics.
Sorry, may I ask some question on the numerics?
Sure.
So for the Hamiltonian constraint that stays 0, do you still monitor that it indeed stays 0 over the simulation, or do you use this like in a standard way, like to monitor the error and then I don't do convergence test or something like this, or?
So the Hamiltonian constraint is it is imposed to be 0.
Okay, but like just at the initial time, or even during the evolution, you still continue to impose it to be 0 somehow?
Yes, that's correct. We impose it to be 0 at all times. Correct.
Okay. Okay.
I mean, you're right. You're right that you might want to worry about errors appearing in other places. So here we're just looking at the horizon, and it appears to be stable enough, which is enough for our purposes for this type of systems that we want to evolve. But you're right that if in more complex systems, you should keep track of other variables. So once again, I am not claiming that this is necessarily the best formulation for all types of systems.
Okay, thank you.
Okay, so back to the physics. The idea was to, starting from an Rn black hole, we have a tachyonic instability that develops into a scalarized black hole. So this we can think of, I'm going to call the U1 symmetric process, meaning we start with a vacuum expectation value of the field, which is exactly 0, and this evolves into some non-zero value. And then we have the second possibility, which is when you start with a scalarized black hole, which is itself unstable, and this is going to evolve into another scalarized black hole, meaning that this process I'm going to call U1 broken, in the sense that the scalar field background is going to be non-zero. So we will numerically evolve the system starting with a background according to this prescription, plus some small perturbation. And the perturbation, because remember that our interest in this system was to explore the consequence of the symmetry breaking. Let us define the perturbation to have some fixed phase. So it's going to be some Gaussian wave packet in the radius. So it's going to be spherical, and it's going to have some phase, some fixed phase. So these are the results of our simulation. So this plot simply shows the scalarization process. So here we are plotting the horizon value of the scalar field, the norm of the scalar field. It starts from 0 in the Reisner-Nordstrom black hole. And it becomes destabilized, and it grows and eventually settles into some non-zero value. So this is the process that I called before the U1 symmetric, where you start with Reisner-Nordstrom, the scalar field is exactly 0, and you end up with some scalarized black hole, so with some scalar cloud. Okay. On the right, we have the case of a U1 broken process. So in this case, I'm going to choose the background scalar field. Remember, we have a background scalar and we have a background perturbation. So this is what I'm indicating here at the top right. We have a background scalar and a perturbation. Because the system is U1 symmetric, you can choose the background in any direction you want. So let us choose it without loss of generality to be along the phi1 direction, along the real axis in the field space.
Sorry to interrupt you. Eugene is
Yes.
raising his hand, so Eugene, if you want to ask your question.
Thank you. So what fixes the non-zero value of the scalar field for large T? You get a non-zero value, 0.12 in your plot. And what fixes this value?
Yes, so
kind of vacuum
there
expectation value.
Yes, so this is a function. I wasn't very careful. This is a function of the charge to mass ratio of the Reisner-Nordstrom black hole that you start with, and the non-minimal and the coupling alpha.
So it comes from X, yeah? I see.
Yes.
Okay.
Yes.
Thank you very much.
I will try to be more careful later with by indicating parameters and so on.
Thank you. Thank you.
Right. So in the U1 broken process, as I said, without loss of generality, I can take the background to be along the real axis in the field space. And in this example, I chose the phase of the perturbation to be pi/2. And you see that, well, this basically highlights the differences between the U1 broken process and the U1 symmetric process. So here in these three columns, we are plotting the norm, the real part, and the imaginary part. So
Sebastian?
this is yes, please.
May I ask a question?
Yes, please.
So is the energy conserved in these evolutions, or is there appreciable dissipation or loss of the total mass of the system?
There's going to be loss. That's yeah. I will talk about that in a couple more slides. Yeah. Thanks.
Okay, then I'll wait for that. There's a follow-up, but I'll wait for that. Thanks.
Okay. Yeah. So this is basically the same plot. So here I'm plotting just the norm of the scalar field. But now here I'm considering two different values of the phase of the perturbation, of the initial perturbation. So in the first row we have theta, the phase is equal to 0. In the second row it is equal to pi. So this is really equivalent to a real scalar. So here I'm simply highlighting what you would observe in the case of a real scalar, where your two possible vacua are either right or left. So this is a system that breaks a set2 symmetry rather than a U1 symmetry. So this is what you would have in the case of a breaking of a Z2 symmetry. Again, there is a preferred the breaking comes because of the background value. So the background value has a preferred direction. So you would not expect perturbations on these two, starting on these two vacua to evolve identically. So this is a simple way to highlight the process of symmetry breaking. I had some movies, but unfortunately, because I had to switch to a PDF before sharing the screen, the movie got lost in the process of converting to PDF. But it was basically the numerical evolution where we were plotting the radial part of the field and the angular part of the field as function of time. So this sort of highlighted the process of accretion because it showed how the apparent horizon grows in time and how part of the scalar cloud becomes ejected to infinity. I'm sorry that I cannot show it. So there's a lot of information in this slide. I apologize. So let me try to go step by step. So here I am plotting the horizon value of the scalar field, phi h, for different choices of the phase of the initial perturbation, okay? So in the first plot, we are looking at the U1 symmetry case. So the initial condition is at the origin. So this is a plot in the field space, phi 1, phi 2. So the initial state is at the origin when the scalar field is exactly 0. You have just a Weissner-Nordstrom black hole, which is unstable. As we know, it undergoes scalarization. And depending on the value of the phase of the perturbation, you can evolve along these curves that we are plotting here. So remember from the figure I showed before, let me go back. From this figure on the left, you see that in the process of scalarization, you kind of overshoot a little bit before you settle into the stable value. So this plot basically shows that, but now in the field space. So if you imagine going along one of these lines, you initially overshoot a little bit, but eventually you settle back into this dot here, which represents the final state. Okay, and you get well, infinitely many lines, of course. Well, I'm not drawing infinitely many lines, but several. But the evolution is identical, of course, because the initial state respects the U1 symmetry. So this is exactly what we would expect, of course. But I draw it anyway to highlight the difference with the U1 broken case, which is the second and third plot. The difference between the second and third is simply the charge to mass ratio of the black hole that we consider. Okay, so the color coding is meant to represent the different values of the initial phase. So the color curves are curves that are actually close to the real axis, whereas the black curves are the rest. So what the second plot shows is that actually there is a sort of preferred trajectory. Most trajectories actually want to be sort of along these I don't know if I should call it a tractor really, but there seems to be some sort of a tractor, whereas most trajectories want to lie in a preferred kind of trajectory. And it's only if you consider initial phases which are small enough, meaning close enough to the real axis, that you get to observe something that deviates significantly from this attractor kind of trajectory. Again, the system, the reason you have this particular feature is because we choose the initial state. So the initial state is over here to be along the real axis. Okay, so remember that this is totally arbitrary. So in principle, this could rotate depending on your initial value of the background. So in the third plot, basically everything collapses. So in the third plot, there's actually all the curves, but they are all hidden behind these two curves. So the observation is that for large enough charge to mass ratio of the black hole, this, what I call attractor, happens to be extremely strong. Basically, all trajectories are immediately drawn, immediately pulled into these attractor trajectories, to the extent that in this plot, you cannot just distinguish them by eye. Okay, so this feature seems to be highly sensitive to the charge to mass ratio of the black hole. So here, I should speed up a little bit, sorry. I think I will skip that, sorry. Let me go to the question about the energy. So indeed, here we are plotting the ADM mass, the initial and final ADM mass. So in the, let's start with the purple. So here, the vertical axis doesn't mean anything. So you should just look at the horizontal axis, which is the energy, the ADM mass. The dash indicates the initial energy, ADM mass of the system, and the solid one is the final one. So there is a bit of loss of energy, indicating the process of radiation to infinity. The purple curve is the U1 symmetric. So this is just an RN black hole. So you just have an initial state and a final state. Now, when you have in the U1 broken phases, you can have, because you have a continuum of different trajectories due to the symmetry breaking, you also get a continuum of energy loss patterns. So we call these energy bands in some sense. Okay, so again, if we look at the orange, so the difference between the orange and blue is just the value of the. This is just for different systems. So here we are varying the horizon value of the scalar, but this will be a feature whenever you have symmetry breaking. So in this case, you also have a loss of energy to infinity. So the fact that the dash curve is a little bit higher than the solid curves. So the solid curves are represented by the whole band, whereas where you have the circles correspond to the phase equal pi. This is when you lose the least amount of energy, and the square represents a phase of 0, which means the highest amount of energy loss. So this leads to a kind of energy band. Remember that here, for simplicity, we are considering perturbations with a fixed initial phase. Now, more realistically, if I can call it realistic, you would expect perturbations to be a superposition of all possible phases, of course. So if you were to observe this somehow, what you would observe is actually the energy band, presumably. So this seems to be a characteristic feature of this symmetry breaking effect that you would not have in say, in the case of Z2 symmetry breaking.
Sebastian?
Yes, please.
So, okay, I now have a follow-up. I see, well, if I understand correctly, your plot, then there's this band of energy loss, meaning that in some cases you lose less, and there's more extreme cases in which you lose more. So can you identify some rationale, some feature for both cases? What drives the system to lose more or less energy?
I think the short answer is I don't know. So I was going to talk about. I think what you're asking if I could have foreseen this feature just by the initial phase,
or interpret it in some way, yeah.
No, I honestly, I do not have any intuitive interpretation. No.
Okay, fine. That's okay. Thank you.
Okay, thanks. So I'm running short of time. Let me try to summarize the second part of my talk. Well, it was meant maybe the last quarter of the talk. Let me see how far I get. So remember that so far we consider a scalar field that was neutral under the electromagnetic U1, but when you have a complex scalar, it's very natural to make it charged under the electromagnetic U1. You already have an electromagnetic field in your theory. You have a complex scalar field in your theory. So it seems very natural to postulate that it should be charged. Now, when you have a charged scalar field, or more general charged particles in a Reisner-Nordström black hole, as most of you probably know, you also have a new effect, which is superradiance. So in this cartoon, I'm representing the idea of superradiance. It is basically a scattering problem. You have an incident wave coming from infinity, and you have a potential bump, a potential barrier, an effective potential barrier. And part of this wave is going to become transmitted, and it's going to fall into the black hole. So the black hole in the tortoise coordinate is at -infinity, and part of the wave is going to be reflected. And it is possible for the reflected wave to actually be stronger in amplitude than the incident wave. So this is what we refer to as superradiance. So this has also been studied in the EMS model. So this is what we are going to consider. The only difference between this and the previous one is that we are promoting the covariant derivative of the scalar field to be a gauge covariant derivative. So we add a minimal coupling to the electromagnetic field with some Q that represents the electric charge of the scalar field. So this system now has a local U1 symmetry, both in the electromagnetic field and in the scalar field. And I just want to make sure we don't confuse the electric charge of the field, little q, with the big Q, which represents the charge of the Reisner-Nordström black hole, of the charged black hole. So this is going to be our background electromagnetic field for the Reisner-Nordström black hole. So there's a specific relation that you can derive that's satisfied by the transmission, incidence, and reflection coefficients of the scattering problem, and it is given by this. So this shows you that it is indeed possible for the reflected wave to have higher amplitude than the incident wave. So this is the so-called superradiance condition that, in the case of a charged scalar field, is given by this condition over here. So what physically, so this is superradiance in equations, but physically what's going on is that you're basically gaining energy. So the incident wave is being reflected with higher energy at the expense of extracting electromagnetic energy from the black hole. So this is very analogous to perhaps the more familiar black hole superradiance process of spin in the context of spinning black holes, where you extract rotational energy from the black hole in order to get a magnified wave. In this case, we are not considering rotation, so the additional energy that you gain comes at the expense of the electromagnetic energy from the black hole. So we would like to, what we're interested in is to study the combination of these two effects. So we have the process of scalarization that arises from the non-minimal coupling, and the process of superradiance that arises from the scalar field being charged. So what we find is that tachyonic instabilities will actually persist when you have charged scalar field in the EMS model. But we also find numerically that there are no hairy black hole solutions in this case. So this results is known in the minimally coupled case. As far as I'm able to say, I was not able to find any no-hair theorem in the non-minimally coupled EMS model. I imagine that it should not be difficult to prove, but I have not seen it in the literature. So if anybody knows about this, I would be happy to hear. But at least numerically, this seems to be the case, that the charge EMS model does not evade the no-hair theorem. So you would not expect to find hairy black hole solutions in this theory, and this is what we find numerically to be the case. So this is good or bad news depending on who you ask. If you're interested in hairy black holes, this would be bad news. But it might be potentially good news if for instance you are interested in the process of energy extraction. So the fact that the scalar field gets fully ejected because you don't have hairy black holes might be potentially interesting from an observational perspective.
Sebastian?
Yes, please.
If I'm just allowed to make a small comment, so you are still considering the model that you presented initially with without any potential for the scalar field. Is that I guess that's the case, yes?
Correct, this one. This is my theory.
Right, exactly, yeah. So, well, the comment which probably you are aware of is that you can get hairy black holes if you introduce self-interactions for the scalar field. But in fact, yeah.
Yes, I agree with that.
Appropriate self-interactions, yes. But yeah, I think that the statement you said, there's indeed you can show to some extent the absence of hairy black holes without the self-interactions. Although there's some gaps here, but perhaps we can discuss that later. But please go on. So I just want to make this point here.
Okay, thanks. Yeah, I would. My impression is that this should not be difficult to prove. But again, I did not find in the literature any explicit statement on this. Yes. So this is our numerical setup, just so that I can show you the results quickly and I can wrap up. So we have an initial state given by an Rn black hole. To make the process numerically faster, we choose the charge to mass ratio to be large enough, so 0.9 in this case. Again, we're going to consider a Gaussian perturbation. Here, I'm not going to be concerned with the phase, by the way. So this is something we would really like to study in the future, but we have not done it yet. So in this case, I'm not going to be concerned with the phase of the black hole, but rather what I want to investigate is more the superradiance, the effect of the superradiance. So we are particularly interested to measure the energy that is going to be emitted at infinity. So for numerical purposes, this means placing an observer at some very large distance from the black hole, 250 in our simulation. And what we are going to calculate numerically through numerical relativity simulation is the final mass of the black hole, the final mass of the spacetime, the ADM mass of the spacetime, and the final charge. So this is our goal. Let me skip this for a moment. So let me show this slide quickly. So this is basically a sanity check that we made where we have no superradiance and no scalarization. So the charge of the scalar field is 0. The non-minimal coupling is 0. And here is is basically a sanity check that we get what we expect. So we have an initial perturbation. So this is a stationary wave packet. So we expect part of the wave packet to travel to the horizon, part of the wave packet to travel to infinity. And this is exactly what we observe. So this first feature here we're keeping track of the energy of the scalar field and the electromagnetic field. The blue curve is simply the sum of the two. So E matter is E scalar plus EEM. There is a loss of energy of the fields when the scalar field reaches the horizon. So you lose that as the energy becomes accreted. There's another loss of energy, this bump at about 200 when the scalar field reaches the detector at infinity, essentially infinity. And there is a third feature, a small feature here that you might see. This corresponds to part of the scalar field which reached the horizon or the vicinity of the horizon, basically the potential barrier, and becomes reflected and this reflected wave eventually reaches the observer at infinity. So this was just a sanity check that we get what we expect. So this is the case of normal superradiance. So in this case, we don't have scalarization. So in this case, you can see the amplification of the scalar energy at the expense of the loss of electromagnetic energy. So again, this is another sanity check, really, that that we are really observing the process of superradiance as we would expect it. So a growth in scalar energy at the expense of electromagnetic energy. Now, the scalar energy eventually decreases in this case because, again, it goes, part of it goes into the horizon and part of it becomes, just goes to infinity, is lost to infinity. This is a third sanity check when there is no, where we only have scalarization, but not superradiance. So this is really what I already showed. The scalar field grows as a result of photogenic instability. But eventually, it also relaxes by emitting radiation to infinity. So this is the interesting case.
My microphone, can you hear me, Jordan?
Yes, I can hear you.
Yes, sorry, it's that my headphones died.
No worries.
So this is the combination of the two effects when we have both tachyonic instability and superradiant amplification. So what I should mention, let me make that comment later. So here we have the tachyonic growth due to the scalarization instability. So it grows initially, and then it continues to grow at the expense again of the electromagnetic field. So this is the process of the superradiant amplification, which occurs even though the total energy of the matter is actually decreasing, as you can see on this top curve. Okay, so even though stuff is falling into the black hole, the superradiant amplification still gives you an increase in the scalar field, and eventually this relaxes as it goes ejected to infinity. So on the right, I just want to highlight how the amount of mass, the amount of energy that you lose through the whole process. This is the same, but with different parameters. So we'll skip this quickly. I will also skip this, sorry. So this is almost I'm almost finished, by the way. So what I would like to highlight here is that the observation we want to make, the observation we want to emphasize is that this appears to be a very efficient mechanism for extracting energy and charge from a black hole, because you are basically exploiting two mechanisms. You are making the scalar field grow thanks to the scalarization process, and all these energies being efficiently ejected to infinity thanks to the superradiance effect. Okay, so this is what we wanted to highlight here. So here on the bottom plots, these are two different values of the scalar field charge as function of the charge to mass ratio of the initial black hole. So you see that you can get a sizable fraction loss of the energy and the charge of the black hole as a result of this process. Of course, whether these values are realistic, that's a different question. Remember that hopefully this will be a useful proxy model to analyze more interesting systems, for instance, rotating black holes that do not rely on electric charge. That would be sort of the hope. So let me summarize. I'm a little over time. I apologize. So we've investigated scalarized black holes and showed that there are scalarized phases of black holes that are themselves unstable to what you might want to call a secondary scalar cloud, and this cloud displays non-trivial evolution as a result of the symmetry breaking. And in particular, I highlighted this energy band sort of characteristic signature. I also mentioned briefly a new numerical scheme that we found to be particularly useful for long-time evolution of black holes. And we have also briefly begun to study the case of a scalar field, which is charge under electromagnetism, which opens the door to the superradiance effect and also the combination of the two effects, which well, this is really work in progress. So I've showed you only some partial results. So we would hope to continue investigating this combination of the effects. That's all. Thank you.
Thank you very much. So no worries for the time, especially because we had some questions in the middle. So it was very nice. Thank you for the nice talk.
Thank you.
So we have more time for questions now, if there are. So well, okay. Let's ask with Miguel maybe. Start with Miguel.
Yeah, can you hear me?
Yes.
Yeah, so I would just like to go back to the question that Jordan briefly asked. Do you have plots for the violation of the constraints during these evolutions?
Not here. I do not have plots here.
Okay, but okay. No, I was curious to see how. Yes, yeah, exactly. So for this kind of for this evolution, so you're showing here the variation in the area, but it would be nice to see how the constraints themselves are doing, especially given this this interesting scheme, right? So I was curious to see how this behaves, how the constraints themselves then behave for such long evolutions.
I agree. Yes, I don't have plots here. I could share them with you if you get in touch. Yeah.
Okay. Do you have them on a paper or something somewhere that I can check?
I believe we did not include them in the paper, but presumably should not. I think we have all the data and should not be difficult to. Yeah, we're happy to share all data about this. Yes.
Okay. Yes. Okay, thanks.
Thanks.
Thanks. So Carlos.
Okay, so first of all, I would like to thank you, Sebastian. I think it was a really clear talk, and thank you for the care in presenting everything in detail. I had many questions actually, but in the interest of time, I'll just ask maybe one or two. When you are discussing what you call the U1 symmetric and U1 broken, so in some cases you see that scalarized black holes are unstable and they evolve to another scalarized black hole. So my question is if you actually did some perturbative analysis also in the parameter space that would show you in which region of the parameter space you would have these unstable solutions. Because as you pointed out, the condition that you might have a potential with a mass square which is negative. This is a tachyon, but it's not necessarily an instability. I mean, this is well known. For instance, in ADS, there's the famous Brightloner-Friedman bound. So a tachyon is not necessarily an instability. This is a lesson that we've learned in many contexts. So, of course, to see an instability, there are more sophisticated methods. And if you calculate the quasi-normal modes of the solution, that would be certainly a token of the instability, but not of the final state of the instability, which is what you can achieve with your simulations. So my first question is this one. Did you actually have some sort of analysis that would tell you where are the regions in parameter space where you expect to have these instabilities in the scalarized black hole states?
Isn't that in your paper?
Well, to some extent, because we didn't do quasi-normal modes, we just do a potential analysis, and this is not completely conclusive. You can see regions which might have, which have instabilities, but there might be regions with instabilities that, or the other way around, actually. I mean, if the potential is positive, then there should be no instabilities. But if it is negative, then it's not absolutely determined, as we were discussing. So we didn't calculate quasi-normal modes. So that's the thing.
I understand. We did calculate, but we did not do a scan of the parameter space. So in this table here, you can see 3 cases for different values of the scalar field charge. So this is the full quasi-normal mode solution of the linear equation. So here we find that the quasi-normal mode frequency develops a real part in the charge case. Well, this doesn't answer your question of how does the phase diagram look. We have not done that. We only investigated specific choices of parameter.
So when you decided to evolve in your nonlinear evolution some solution, you just chose it randomly, or were the ones where you found that there would be growing quasi-normal modes?
So it was a little bit random, but it was also motivated by your plot. I understand what you say, that your plot is suggestive but not definitive. So we took that as a kind of prior indication.
Okay, fair enough. Well, maybe if there's someone else to ask questions, I will give the stage to them, or else I can ask another question.
There is a question by Romain, but afterwards we can come back to you if you still like.
Sure. Yeah, please go ahead. Yeah.
Yes, can you hear me?
Yes.
Yeah, okay, so first of all, thank you for your presentation. It was very nice, and actually I read your paper a few weeks ago, so I had things fresh in mind, which was nice. And I have just a question to make sure that I understand everything correctly. So your initial condition for the U1 broken process is the same as the final state for the U1 symmetric process, right? Or not?
No, the final state. No, we do not. I'm not sure I understand the question. We do. I don't think we impose anything on the final state.
My question is, if you take Reznor Nordstrom and do your evolution, then you obtain a scalarized black hole, right?
Right.
And then if you take these scalarized black holes and apply the same perturbation, that will become the second process that is U1 broken.
No, the initial conditions are different. So the final state in the U1 symmetric, these are stable hairy black holes.
Okay. Yes. Okay.
Yes. Yeah. So the initial conditions, they are for sure different.
Okay. Yeah. Okay. Yeah. Okay.
Yes.
And the final state of the U1 broken process, it is stable. Okay,
stable.
So if you just take the end state of the U1 broken process and just repeat again perturb it, it will not decay to anything else.
Correct.
Okay. That's clear now. Yes, thank you.
Thanks.
So I see now that Eugene also has his hand raised. So maybe Eugene, if you want to ask.
Let's go for Eugene, of course. Yeah.
Thank you very much for a very interesting talk. I have a minor question. On all your results, the scalar field vanishes in the far away asymptotically, does not acquire a vacuum expectation value, no? Scalar field.
So, well, in the If you're asking about
far
the
field.
initial,
No. End state. Well, when you have hairy or so result of evolution, scalar field. When you get hair, for this broken phase, scalar field far away. What's the behavior? Goes to zero.
Do
you get a vacuum Do you get a vacuum expectation value? Because here it looks like you get a vacuum expectation value, for example.
What is the value of the scalar field at infinity? No, it does go to zero. It does go to zero, yes. Yes.
Okay, thank you very much. Thank you.
Thanks.
Okay, thanks, Eugene. So I think, Carlos, you can, can ask your question.
I have many questions, but I'll just ask one and then we can finish. Sebastian, so all you've said is in spherical symmetry, which is fine. Of course, that's what we want to analyze first. Now, one of the sort of surprises that we've seen in a similar system, which is not exactly like yours, which is when you have your last model without the non-minimal coupling between the complex scalar field and the F, but with self-interactions for the scalar field, actually sextic self-interactions. So in this case, there are hairy black holes. So for the simplest case, I mean, and of course you know this, there's this Mayo-Bekenstein theorem that to some extent covers the minimally coupled case without the master, so the master maps complexity. But we found that in the case with a minimal coupling between the complex scalar field and the electromagnetic field, and in which the scalar field can have self-interactions, there are hairy black holes. And of course, first we looked at the spherical case. And recently, well, we've tried to see how these are or not stable in fully nonlinear evolutions. And it was a little bit surprising, although with the wisdom of hindsight, this becomes clear, that although they are stable against spherical dynamics, they are unstable against non-spherical dynamics. And in that case, actually, the black hole wants to eject from the cloud or the hair. In this case, it's a boson star. So, but so my question, which probably you will say, well, we haven't thought about that, and that's perfectly fine, is that there are cases in which the spherical dynamics is really not capturing the most important dynamics of the system. And we say it's stable. Typically, we say it's stable against spherical modes when we calculate quasi-normal modes or even in evolutions. And there are circumstances in which, even for a spherical black hole, hairy black hole, there's very non-trivial, non-spherical dynamics. So this is kind of a comment, but also a question to you, if you've thought or conceived anything about non-spherical dynamics in this case. And, well, sharing with you also this last result that we've obtained, which I think may be of interest to, although not being exactly the same as similar system.
Yeah. Thanks for that. I'm definitely interesting. So I actually have one of my PhD students. He's actually working on the case of vector field, which of course requires non-spherical perturbations. It's only interesting in the non-spherical case. So he's actually working on that right now. So I'm definitely interested in that in your paper. So I'll have a look. Thanks.
Sure. I can send you a message in case you don't find it. Just send me a message and I'll be happy to discuss it with you.
Okay. Sure. Thanks.
Thank you, Sebastian. Thank you.
Thank you.
Thank you. So, are there more questions? So I think, so we said that people enjoyed the talk, but I think it also showed in this very rich session of questions. So once again, I'd like to thank you for the talk and for your answers to the questions. So thanks a lot again.
Okay, thank you very much.
And so if there's no more question, I'll stop the recording here and see you all next week. And yeah, thanks a lot again, Sebastian, and hopefully we can meet also in person eventually.
Yes, yes, please. Thank you.
Thank you, and bye-bye, everyone.